Hope you're enjoying the Voxed Days 2017. When it comes to running Java applications on very large heaps, the release of Java 9 probably brings the most impressive improvement ever. It will be possible to operate heaps of terabytes and more. And in this session, I'd like to tell you how that happened. My name is Nida. I'm leading the technical team of ActiveViam in the APAC region. Our R&D teams, based in New York and Paris, are building a product called ActivePivot. ActivePivot is an in-memory analytical platform fully written in Java. I'm here with HonWeng. Let you introduce yourself.
Sure. Hi all. My name is HonWeng. I'm a senior consultant with ActiveViam based in Singapore. So the improvements to Java 9 that both Nida and myself are going to review today are a result of a partnership between the Java team at Oracle and ActiveViam. Oracle and ActiveViam met at the end of 2014 when a common client of one of the common client of ours put us in contact and threw us a challenge. Can we run ActivePivot application on a JVM with more than 10 terabyte of heap size? For this purpose, a joint team was created, and we built a prototype credit risk application running on Oracle M7 with 16 terabyte of RAM. The initial result of our work was presented at Java 1 2015, where it drew a lot of attention. As a result, Bernard Traversat, the Vice President of Software Development for Java, decided to strengthen the partnership. Engineers from both the company, Oracle and ActiveViam, started to work together to improve garbage collection, targeting large-scale applications. Thomas Schatzel from the JVM team is in charge, and today, at Vox Day 2017, we are really talking about his work which all of us will soon benefit when Java 9 is released at the second half of 2017. Nida?
That's a very exciting collaboration. Indeed, this multi-terabyte ActivePivot application HonWeng mentioned, and we have presented a year ago, has become the reference use cases for the JVM engineers working on the support of large heaps. And that will be our baseline for the result we will present to you today. Just to introduce the use case we were focusing on, it was related to what we call a credit risk. Most of our clients are banks, and credit risk type of application will require a huge set of data. Credit risk is no more than, for a bank, evaluating the amount that the bank is going to lose if one of the counterpart is defaulting. To do that, you need to do a lot of simulations. Actually, we consume those. ActivePivot is consuming those simulations from the risk engines that the bank has. You do thousands of simulations in the future point time, and then on every point, you do the evaluation of your portfolios and positions. This is how it works. So this requires teras of data to be aggregated. So this is why that use case was really relevant to challenge the JVM on large heap. So let's see our agenda today. First of all, I'd like to share with you our view of the in-memory computing in the Java world and why it matters. Then we'll share our experience of writing Java code that runs well on terabyte of memory. But as soon as possible, we'll get into the heart of the matter for this presentation, the improvement made for the Java 9 that have been made to the garbage collection to unleash large memory applications. So, how important is this in-memory computing story? Does it deserve all the hype? After all, the idea of a CPU loading data in memory has been around since the beginning of computer science. But in the past, what we were doing is like loading a chunk of data in the memory. Between the 80s and today, the price of memory has been divided by 1 million. At that time, no one could imagine loading the whole set of data that an application needs in the memory. But today, almost everyone can do it. It's not even an investment. With a snap of a finger, you can go, for instance, to Amazon Web Services and get an X1 instance. X1 instance has 2 terabytes of RAM. So all the data technology we learned now exists in memory. Maybe you're familiar with some of them. SQL databases, such as VaultDB, will record transactions faster. SAP HANA will execute analytical SQL queries faster. Key value store, such as Redis, Hazelcast, Oracle Coherence, will have access to the element faster. And finally, Apache Spark speeds up big data batch processing, but storing intermediate results in memory. So everything you could do before, you can do it now faster. But is that the end of it? We don't think so. All businesses have their rules and formulas to quantify how well they run. Most businesses run those calculations once a month or once a week in spreadsheets before the board meeting. But what will happen for those businesses when they realize that they can run all those calculations every time on live data and anytime, all the time? The in-memory computing will not merely accelerate the practices, but it will transform the way we do business. So let me give you a few examples. As I mentioned, for the financial institutions, the bank, they can have this type of application, like credit risk application, running all the time on their portfolios, evaluating the risks. So this will give an insight for the traders, for the sales, to take decisions on the spot. No need to wait for the batch to run overnight and to take the decision the day after. Remember what happened in 2008 when Lehman defaulted? All the financial industry were in crisis and everybody wanted to evaluate what is my loss. For the e-commerce, marketing teams and retailers are in charge of putting the right price on the products. But those prices, they depend on the stock level, time of the year, the price of the competition. So what will happen if you have everything loaded in memory and you can, in a dynamic way, adapt those prices according to what the competition is doing? By doing so, you enter the dynamic pricing era. And I'm pretty sure this is what companies like Lazada will do when Amazon will start in Singapore. Because without doing so, you will lose the battle. Last example is related to the supply chain. Say you have, just giving you like a real example that we lived, some of us lived here in Singapore. Sudden weather change, haze coming to Singapore, and everybody's running short of haze mask. So if you have the ability to order or to reroute some stocks of masks in the region and then bring them to Singapore and take the decision right now, that will help. You can also do simulation and say, what if tomorrow there is a haze? Am I able to bring masks for the whole population? So this is something that could become critical. Actually, there are many more striking examples that I can bring from our client use cases. But here we're talking about technology. So what type of technology that we can use to write a solution that is performant? When we start writing the product 10 years ago, the shortlisted languages we were looking at were C++ and Java. I know that some will suggest some other languages, so let's keep this for the Q&A session. by choosing Java, we wanted a language that runs everywhere, that is versatile, safe, allow us to extend it easily, to implement use cases in an easy fashion with a huge community. For instance, Java, we estimate the number of users, developers using Java, like 20 million developers, so a huge community. And then a language that allows us to do complex calculation. Because here we're talking about SLAs, we're talking about sometimes nonlinear aggregation. We're not doing just simple click count that we can achieve with SQL. So we're more close to high performance computing type of use case than SQL use cases. So this is why we picked up Java. And we don't regret it. We're really happy with that choice. So now that the stage is set, let me tell you more the effort we did in the R&D, and I will try to summarize 10 years of R&D efforts in 2-3 slides. So first of all, to run Java on a huge memory, we start by controlling the memory. By controlling the memory, I mean we start storing some part of the memory of heap. For the use case we mentioned earlier, of the 16 terabyte, we had 3 terabyte stored on heap, and the rest was off heap. Of course, that removes some pressure from the garbage collection. This is why some of the solutions running on a huge set of memory written in Java, they use this off-heap technique. Also, some of our internal structures, like the columnar databases, are also stored off-heap. Basically, all the primitives are stored off-heap. Also, to control this memory allocation, we do some system calls, like mmap, and we implemented our own malloc that fits our allocation pattern. The second part was related to parallel programming. For that, we used all the known tricks, like fork join pool, lock-free data structures to minimize the contentions. And we introduced the design where we were partitioning our data to align it along the cores. More than that, we control where the allocation happens. As you know, the big servers nowadays, they have what we call non-uniform memory architecture, NUMA. So what we do is we control where every processor is allocating the memory. We try to stay in what we call the same NUMA node, and we avoid communicating cross nodes. Because if one thread is getting the memory, is getting the data from another NUMA node, will degrade the performance. Don't forget, our engine is running fully in memory. By doing so, we maximize the memory bandwidth. So I'm realizing here that I'm just summarizing a lot of concepts in just a short time. So if you're interested to see all the efforts we did to run our Java engine on a huge memory set, like this of heap, how we did the call to the, how we allocated the memory of heap, the call, and how we were NUMA, how we coded our software to be NUMA aware. I invite you to look at either Java 1 conference 2015, where we're presenting that, or for those who are in Singapore, there is engineers.sg, where we were doing a talk 1 year ago. So let's talk a bit about the garbage collection now.
Thank you, Nida. So basically what was shared just now is just some of the techniques that ActiveViam has applied application coding-wise, how we actually managed to build an application on running on a large heap of memory. But of course, in terms of coding, it can only go so much as how the platform can support it, and that is where the G1GC comes into the picture. So when we talk about G1GC, basically up until 2015, it has not really been tested on very large heaps. And when I say very large heaps, I mean 1 terabyte of heap or more. Of course, that was the goal of the JVM team, but it is more for the longer term. However, with the rise of in-memory computing that Nida has just mentioned, it has made a strong case for improving the G1GC even further, and of course, this helped to reprioritize the improvement, the process to improve it. Now, we mentioned about the prototype that we built, the credit risk application. Now, this application has been used by the JVM team as a benchmark application, as well as to reveal some of the shortcomings with the G1GC, and ultimately it is used to tackle those shortcomings as well. But the story of G1GC started even before that, so let me try to put things into perspective for you guys. Garbage collection in Java has the most impact on overall application performance. That is how important it is. But Java applications have been growing faster than GC could adapt. Applications nowadays, they use more memory. They allocate more objects from more and more threads. And the amount of time that an application must pause to allow the JVM to perform the GC has become somewhat totally unacceptable. So, with the previous GC strategies that was employed, the pause time were actually proportionate to the size of the heap. That's why they are actually obsolete by today. And it has been replaced by techniques that make use of what we have today, which is larger memory and, of course, multi-core processors. The G1GC architecture represents this renewal. With G1GC, the heap is divided into regions that can be processed in parallel. And each of these regions can be assigned a specific policy, one for new objects and another for long-living objects, for example. Do bear in mind that G1GC has been in the works for years, and it has been available since Java 7, but it is only reaching its maturity now. It comes to a certain, it may become the default garbage collector for Java 9. Okay, before we jump into the improvement that was made for the G1GC, let me just give you guys a brief overview on how G1GC actually works in a real application. So as I mentioned, G1GC divides the heap into regions of equal size, and memory management is actually done at the level of these regions itself. So when a Java application runs, the thread will instantiate new objects, and some of the regions are used to allocate these new objects. The regions are what is known as the young generation. So basically, here, more new objects are created, and then the young generation will just continue to grow and grow until it is full, at which point the G1GC will stop the application, wakes up the garbage collection thread, and it will proceed to clean up the young generation. Most of the objects allocated by the application are used for a short time. So statistically speaking, when the collection begins, only a small fraction of these objects are still alive. So what G1GC does is that it will locate these objects which are still alive, and they will be evacuated to other regions, leaving only garbage in the region of origin that can be cleaned up. Do note that all this must go extremely fast, because I can't stress this enough, because it is actually a stop-the-world application, which means application is just stopped while the young collection is happening. So what was noted is that this young collection is not performing as fast as we would like it. It's not just simply not fast enough. So in a moment, Nida will share with you the specifics on why it is not fast enough and what was done to improve it. The objects that will survive will be evacuated into other regions, which is referred to as the survivor region. Technically speaking, the survivor region still belongs to the young generation. So when the next young collection happen, and if there are still objects alive in these regions, they will be evacuated again. So this will happen the evacuation during young collection will happen for a few times until what I mean is after it has been evacuated for a few times, these objects will be promoted into the O region. Now, basically in the O region, these objects will not be it will not be collected. It will not be collected during the young collections. The idea here is that once it has reached the old generation, it will stay alive for a long time. And the continuous process of evacuating them into new regions will actually degrade the performance further. So here, what happened next? The application will go on like this while there is still free memory left through a series of young-only collections. Of course, the old generation will continue to grow until it comes to a certain point that, it reach a certain threshold that it tells the G1 that, hey, you guys better be looking at the O regions as well. Now, this is where the interesting stuff happens. Basically, G1 cannot brutally clean the O region inside the stop the world pause. It is just, it may pause the application for just too long. So instead, what G1GC does is that it tries to do as much as possible while the application is still running. First, it will need to mark the objects that are still alive in the O regions and collect statistics about which O regions contain the most garbage. It will then need to select a number of those regions and collect it together with young regions in what is called the mixed collection, which is basically the last phase in the grayed out box. So what you see here is just some of the phases involved in G1GC, and it will actually move towards what is required, the mixed collection. And on a side note, I'm sure most of you already know this, but G1GC deals with garbage first, and that is how the name comes from. Garbage first is shortened into G1. But as I said, I'm sure most of you would already know this. So next, the marking phase. It will take a while, but note that it is done concurrently while the application is still running. So while the marking is proceeding, there may be several young-only collections in the middle. So basically, as you can see from the slide here, concurrent marking is the phase is below, and in between, as I mentioned, there may be several young collections. Now, when the concurrent marking is done, there is a stop the world pause, which is called the remark. This is to help the completion of marking and to ensure that all the objects that they have located, all the live objects within the O region, including those objects which were created by the young collection in the middle. And then there is the statistic collection phase. Now, again, this is run concurrently with the application. Here, what G1GC does is that it collects statistics about how full each of the O regions are. After the statistic collection, there will be another phase, which is a stop the world process, which is called the cleanup. And then it goes to one last young-only collection. The purpose of this phase is to free up as much space as possible in anticipation for the upcoming mixed collection. Now finally, we have reached this is where the mixed collection can begin. Here G1GC will evacuate and collect the young regions as well as a set of O regions that it has identified. This process is going to happen for a few times until all the O regions that G1 wants to collect are processed, and at which point we are back to square one. Now, I'd like you guys to actually take a short pause, try to digest the phases here as much as possible, because, okay, pay special attention to the young collection as well as the concurrent marking, because next Nida is going to share with you some of the specifics as to what are the improvements done to these two phases. Nida?
Thank you. Okay. Now that you have an overview on how G1 works, what we noticed when we were playing with our application is that some part of the G1 scale pretty well, but some part not that much. Last year, when we were collaborating with Oracle on our use case, we started on a static set of data, and we were stressing that set of data by firing short queries and then other queries that require a lot of aggregation. What you see in this benchmark is, like, for the short query, the average pause duration is around 5 seconds. But for the other, use cases, that sometimes the pause is close to 30 seconds. However, we never hit what we call the full GC, which for this size of memory, almost means game over. But the idea is, this scaled pretty well, but we were not happy with those pauses that are close to 30 seconds. Because remember, the use case we address is an interactive application. We want things to run smoothly. When you fire query, to have something that runs in almost a few seconds. By having 30 seconds of pause, then our clients won't be happy. Being in contact with the JVM engineers, we start looking at the first phase that HonWeng mentioned, which is called young collection. Since for this use case, we didn't change the data set we were working on, which means the data set is already in the old gen. The old gen won't change much. So what led us to those pauses, those 30 seconds plus pauses, are only related to the young collections. So this is what we start doing, is focusing on the young collections. So how does the young collection work from the internal? So usually the GC threads start looking at their stack, and then they start from the root objects, and then they follow the outgoing references. And every time you find a live object, you evacuate it. However, well, one reference brings another reference and so on. So what the thread need is to store, what they do is they store the references in their public buffer. When the public buffer is full, they store the references in the private buffer. By having the references in the public buffer, we enhance the work balance. Because sometimes when the thread is working on its private buffer, if the public buffer is full, other idle threads who finished their job of evacuating, they can do what we call work stealing. So this is a common pattern that you find in the fork join pool, for instance, to have a good work balance. But the thing we noticed here that could be enhanced is that some threads get flooded. They get flooded when they were processing a large object arrays, which brings a ton of references. By having those huge number of references in the buffer, they keep looking at them, trying to evacuate them. The public buffer remains empty, and then you have only one thread working, for instance, focusing on its private buffer, trying to evacuate the object, and other threads who finished their job, they're looking at the only thread who is working there, trying to finish this young collection. So maybe you notice such behavior when you sometimes look at a thread dump and you see only one thread is working and other threads are all idle. So then there is an enhancement that could be done, which is working on the cause of references flooding. So instead of copying all those references coming from large object arrays, what the JVM engineers at Oracle did is just to copy the reference of the thread or process those large object arrays by chunks. Also, when a thread is focusing on its private buffer, from time to time, that thread will fill its public buffer, so other idle thread will come and help. By doing those two enhancements, we reached the following benchmark. So as you can see in blue, those are the new poses after those enhancements that has been done on the Young collection. I'd like to highlight the one in the middle, which we're happy with, because we divided by sometimes like 5 to 20 times. We were 5 to 20 times shorter in this Young collection phase. And this, for interactive applications, it changes everything. That was the first improvement that has been made, so on the Young collections. However, ActivePivot being an interactive tool that is able to ingest data that comes along the way during the intraday, that means that our tool is not a read-only tool, even if that use case was in a read-only mode, focusing on static set of data. What we wanted to do is reshuffle and refresh the data that is stored in our database while doing the GC. And that didn't happen well. So that was a disaster 1 year ago, because the phase that is the concurrent marking phase, we're spending too much time there, and then we were not able to do the mixed collection, and then the old gen get full, and then you hit the full GC. And then the game is over. So something has to be done on the improving mixed collections. That is probably the most important improvement that has been made on G1 for the Java 9. So let's have a look. Actually, we did 2 improvements. If you remember well, before doing the mixed collection, we have to do the marking. There is the marking phase that happens in parallel with the application. For that marking phase, you need marking threads. The marking thread, they work same as the GC threads. However, instead of evacuating objects, they just mark them for the later on mixed collection. So same, we start from the root object and then we follow, and then if there is any live thread, any live reference, live object, we will mark it. The way this works in the internals of the JVM, it works as follows. Actually, you have a sub-sampling of the Java heap, and then every 500 bits of the Java heap has, you have a bitmap index for every thread, and then if there is a live object in that portion of 500 bits, you set the bit to 1. So every marking thread has a bitmap index that will just index the regions that have live objects. That works well when you have few marking threads. But on a huge application, you need hundreds of marking threads. And the fact that you have a bitmap index per thread, that was a disaster, because that bitmap was waiting sometimes a few tera, and that didn't work. What the JVM engineers did is, instead of having 1 bitmap per thread, they totally changed this part, and then you have 1 common bitmap in a lock-free type of structure. For that, they used compare and swap, CAS, if you're familiar with that. And then all the threads can access to that bitmap. Instead of having 1 bitmap per thread, and then at the end you have to merge it, now you have just 1. So that was the first thing that has been made for improving the mixed collections. The next thing that has been enhanced is related to the work balance. What they noticed for the marking thread is that they have their private buffer, but they also have a shared structure where those threads, they can store the reference, and then the other threads may help. However, this structure was guarded by only one global lock. So only one thread at a time can access there. So then, from that, they moved to a lock-free structure to enhance the work balance and minimize the contention. With those two improvements on the mixed collections, we will be able to move to 50 times, having a marking 50 times faster than before. As you can see here, we have side by side the read only, so that was the one related only to the young collection, and then the read and write. And for the read and write, what we were doing, we were changing 1 terabyte of data. So behind, you have a process that is bringing in new data into the system, removing the old data. So there is some resources that are allocated to refresh the data, plus answering the queries. So this is what we had. If you put side by side the read and write and the read only, you notice that we have less than 50% in terms of scaling. So that means that the marking collection and the mixed collection, they were working well. Remember before I told you that this didn't work at all. So with this last benchmark, we're reaching the conclusion of this talk. Let's focus on some takeaways. Actually, with the effort that has been done and the collaboration that has been done between us and the guys who are writing the JVM and the garbage collection algorithm, we didn't change the philosophy of the G1GC. What we did here is some engineering. And this engineering that has been done, you will find it will be for everybody. You will find it in the OpenJDK, you will find it on the hotspot when it will be released in 50 days. And Thomas Schatzel, the guy who oversees this work, told us that during the lifespan of the JDK9, what he expects is to reduce those poses in 1 second or less on a huge set of memories. So if that happens, you will probably see us again on stage to talk to you about that. Do you want to add a conclusion?
Okay, let me try to just wrap things up for you guys. What Nida and I have actually done is that we shared with you guys some information about the rise of in-memory computing. We shared with you guys some of the techniques that ActiveViam has used on how to build an application that runs on large heap of memory. And then we presented just a brief overview on how G1GC works, and most importantly, the improvement, enhancements that was done on G1GC, which will be available in Java 9 for you guys. And as just a final reminder, if you guys just visit the site of Java 9 Countdown, you will see that Java 9 will be available for all of you in 54 days. So, thanks.
Thank you. So we're open to questions.
Generally, high demanding applications using a large heap will have a penalty like large pause times. How are you going to deal with those kind of things in G1GC?
So what's the question exactly? This will be minimized with the JDK9. The efforts that have been done on the G1GC for JDK9 is to minimize those poses.
Yeah, because if you're using a large heap, right, defaultly the pause time will be very high. For example, like we are using a high demanding website where the pause time is not at all tolerable. In that case, how do we deal with the large heaps?
Okay, actually the approach is like for any, here what you're talking about is, I'm having a pause in my garbage collection, right?
Yeah.
So if I were you, what I will start first of all is to print all what we call the ergonomics, the G1GC ergonomics. Okay, so you turn some flags on, and then you will start seeing where the pause happen. Does it happen in the young collections? Does it happen in the mixed collections? Do you have humongous objects? You look at the C set, the R set. Maybe you have to know the default values. You have to maybe resize the regions. There are many ways of tuning the G1 and the JVM in general. That has been around like even before around JDK 7, 8, and now with G1 GC that is gaining like attention in the JDK 9. So you have first of all to understand where is the bottleneck.
Generally, most of the things, right, it will be in a concurrent mode. It won't stop the application. So, but if you're using a full large heaps, that will be like a stop the world kind of thing. So that will be a bit hard to handle.
Sorry to interrupt, but my first question to you is, are you using G1 GC?
We are about to use.
Okay, because if you switch to G1 GC, you will notice that there is a significant performance improvement just by switching to G1 GC. So what we are presenting here is on top of what is already good, we have actually enhanced it just for applications that runs on huge heap sizes. So first of all, do try G1 GC. You will notice the performance improvement immediately.
Actually, when you look in G1 GC, the Java literature and some blogs, people will tell you, don't tune anything for now. Use it as it is. Then, of course, like others, you can start doing some tuning. For instance, what the AHOP, which is the initial heap occupancy percent, this you can lower it. Before it was like 45% for the other GCs. For G1 GC, it becomes adaptive. So you can tune that and bring it down. For instance, for our application we're playing with, if you see our previous talk, we had maybe 20 flags that we added in the JVM. We didn't use it as it is. So we had to lower that occupancy. So as far as you have your heap occupied with 10%, you start the marking. You're forced to start the marking. You have some other metrics where we can say, I'm expecting the collection to happen in this max post time. So you have many flags, and you can take it offline. I can give you some good references, some blogs you can look at. But the idea is you have to know your application, you have to know where is the bottleneck, and you have to know where is the bottleneck in the garbage collection part. Either if you use parallel old or CMS or even the G1. I'm not saying the G1 is a silver bullet that will solve all your problems. You have to, it's related, it's per application, and G1 as well can be tuned.
I know, thank you. Because I'm JVM giving it.
Oh yeah, definitely. Yes, please.
In a graph, right, you have several policies. Are all the policies stop root close, or is some of the policies can still run application?
So go back to the graph. Are you which one?
Before
you mean
the G1 GC.
You mean some? Sorry.
Still back.
You mean this one?
No, back.
Previous slides.
Previous one.
Before that, when you talk about how the G1 GC works with regard to the application.
You say stop, huh?
Yeah, this.
Okay. What you see here is a stop the word.
They are also stop.
But stop the word doesn't mean stop the word forever. It can be stop the word for milli or nano. But when we say stop the word, this is the way G1 GC is working. Okay, like to do the young collection, you have to stop the word, but you have to stop. Like there is, when we say stop the word, it means like pausing the application. As you know, to do the collection, you have all your threads have to be in the save point. Sometimes you have to stop what you call the thread mutator to do the collection. You cannot. The only thing, roughly, that you can do in parallel with your application is the concurrent marking. All the others, you have small pauses. And of course, if you're on a huge, this is what you notice if we're on a huge memory. And then when we had stop for 30 seconds for the young collection before we start looking at how to enhance it. That 30 seconds was too much. So that was a quick win for us, and especially for the JVM, Oracle JVM engineers. So all those, yeah, there is a stop the work, yes.
Is there a term to configure how many threads you can use for marking thread?
Yes, this is something you can tune as well. There is a default, I don't have it on top of my head, but by default you have like a ratio from the available threads that will be allocated to the marking, a ratio from the available thread that will be allocated to the garbage collection. Of course, yeah. You have to know, you can find this on Oracle website, all the default parameters, like the initial heap occupancy percent, the number of threads for marking, the number of threads for collecting.
So I have two questions. The first question that after the improvement that you guys have implemented, do you think the Java 9 G1 JC can be comparable to the Zing Azure JC?
Good question. Okay, okay, we used our product center or R&D is we're not. We collaborate with Oracle, but we collaborate also with Azure. For those who doesn't know what's Azure, Azure is used to be a spin-off for Sun Microsystem. They did their own JVM, which is a fork of the hotspot, and they have a JVM called Zing, and they have their garbage collection algorithm is called C4. We tested Azure. The poses, when we tested Azure in 2015, where the poses were like in second for the hotspot, they were in millisecond for Azure. Azure claims to be poseless. It's not free, you have to pay for it. It claims to be poseless. However, what we noticed is that when we were firing the queries were, the response time was better with hotspot. Why? Because Azure is using maybe 10 to 15% of the CPU power. Because there is no magic. Don't believe in magic. And there is something that is happening behind the scenes. So if there is a pause, if you're poseless, it means like you keep doing some stuff. And this is what they're doing. So yes, we tried Azure. But Azure also they're improving on that. And I think at the end of the day, the two VMs will be comparable, I guess. So that was the first question. You said you have two questions. Right?
Yeah, the second question that when you have a heap size reach 16 terabyte, do you use the normal page size for Linux or you use the huge page size for Linux?
Come again?
I'm talking about the operating system.
Yes.
Because for the normal operating system, Linux set the page size is
yes.
around 4 kilobytes. Do you set it to be higher or you still use the normal standard 4 kilobytes?
I don't have exactly the parameters in mind, but I know we're dealing with something related to huge page size. I can find you that. But yeah, that matters. That matters. Of course, that matters. Yes. I can let's say go offline. I can find you what we did. I can find you that. But there is of course there is. You have to enhance, and like you have to take the most of the OS as well. Actually, when we were testing this was on a Solaris, but we tested also on Linux. But yeah, page matters as well. Please.
After every collection, young generation and old generation is trying to increment the size, right? Initially, it is not committed fully. It is allocating the size, but after every collection, it is trying to increment the generation sizes. So my question is, after doing that increment, after collection happens, if the JVM knows that it has more than enough memory that it needs to calculate the algorithm, will it give that memory back to OS?
But first of all, I don't know, as I mentioned, it does not increase the size. What happened is you allotted a set of a fixed set of heap, JMX, etc. What the G1GC does is that it split it up into regions of equal sizes. Now, when young collection happens, or even the old collection happens, it does evacuation. It takes the objects which are still alive, put it into other regions.
So by setting these parameters like XMX, it won't affect, right?
No, actually XMX and XMS is just what your initial allocation. And usually, side note, set them to the same value. Okay, this is the best practice. Don't set, especially if you know that you will reach something close to XMX. Don't like put 100 and then 500, both 500 gig or meg or whatever. Okay, and then G1GC, by doing what HonWeng said, evacuating means I move the object from one region to another region, and then to do what we call compaction. Actually, it's the first time in the garbage collection that we're doing incremental compaction. Before, we were like, if you're used to serial or old gen type of GC, you were stopping everything and then let's do the compaction. Here, the compaction will happen incrementally. This is quite unique, this mixed collection. This is unique only to, this is proper to the G1GC. So incrementally, you're doing the compaction without harming the application. Because hitting the full GC would be a bad experience for your end users, definitely. And every time you keep looking at, okay, those regions, so I put everything, I evacuate everything to this region, and then I compact and I clean. Sometimes one of the phases when you see the cleanup phase is like, oh, this region is all full of rubbish. I clean it. Okay, so you have all the mechanics about the fact that everything is regionalized. It makes the work easier. Before, I'm like the regions don't have to be contiguous. You can have a bit of yang here, a bit of yang here, a bit of yang here. Before, a long time ago, everything has to be contiguous for some JVMs. So this brings more flexibility. G1 is really something that will change the life of someone who used to work on application but was suffering from the GC activity, definitely. Are we done? Okay, thank you. Thank you very much.